Welcome to our discussion of the precise definition of a limit. So when we talk about the precise definition of a limit, we want to try to quantify the accuracy of a limit by determining how close we want to be to L and then backing out how close that requires us to be to x is equal to a to achieve that accuracy. So we let f be a function defined on some open interval that contains the number a. The x value a is the value that we're interested in. Sometimes, of course, right at a, the function might be undefined, but we can still have a limit that exists as we approach a from the left and the right. So we use the Greek letter epsilon, so that's a lowercase epsilon, and the lowercase delta. So those are drawn. Let me just show you how to draw those. So an epsilon, you draw it like that, and a delta, you draw it like that. Because we talk about epsilon and delta, those are the very small numbers that we're going to use to quantify how close we're getting to L and how close we're getting to A. We commonly call these proofs epsilon delta proofs. So here's the definition that we're going to use. If for every number epsilon greater than 0, there is a number delta greater than 0, such that the absolute value of the function f of x minus the limit value is less than epsilon, whenever the absolute value of x minus a is between 0 and delta, then we say the limit of the function f of x as x approaches a is equal to L. All right, so we're going to work with this definition, which is a little bit daunting to understand at first glance, but after a while it's not too bad. So in order to understand what's going on with this definition, let's look at a diagram. So we have some function f of x, and we're saying here that as we adjust the value of epsilon, that's the closeness of how close we are to the limit L, then the value of delta, that's the closeness to the value a, is affected by the shape of the graph of the function. So what I mean by that is that if we make these two yellow lines get closer and closer to a, where they hit the graph of f of x and then go over horizontally to the y number line is going to change. All right, so the closer I get to this value of a, right, then the closer I'm going to get to the value of L. And then you could look at it this way as well. The closer you get to the value of L, then the closer you're going to get to the value of A. So when we talk about quantifying limits, we're talking about setting a value on this closeness, either setting delta and backing out epsilon, or setting epsilon and backing out delta, either way. So then the next thing I want to talk about is how do we make sense of why these absolute value bars are in our definition. So let's look first over here at the absolute value of x minus a is less than delta. All right, so that goes back to the absolute value definition that we learned maybe a while back. So let's say this is 0, and we want to have a distance to one side of 0 and the same distance to the other side of 0. So it makes sense to say that the absolute value of x is the distance from 0 on the number line. That's because it doesn't matter whether you're on the negative side or the positive side, you're still going to be the same distance from 0. So if I add in there right beside x a minus 0, it would look like that. So that's the distance x from 0 on the number line, either to the left or to the right. Now if we look up here at this inequality statement here, and instead of having a 0 here, we can put an a here, and we can put an A here, right there. Now we can reimagine this statement to say the distance from A is the absolute value of x minus A. So that's the distance from A on the number line. And if we put this delta right here to signify this distance from A, which is the same on this side and this side, we can interpret this statement as saying the distance between x and A is less than delta. Okay, in this statement it's equal to delta, but the interpretation of this statement here is that the distance between x minus A is less than delta, and we have that in our definition right here. All right, so we always want it to be bigger than 0, so this part over here is not really that significant to what we're going to do next. All right, now let's talk about this. So that's over here. So we can say this one is the distance between f of x and L on the y number line this time. So we're talking about a y-axis this time. All right, so we can interpret this as saying epsilon right here is the distance between f of x and L on the number line. All right, so by f of x, what we're talking about is this value here and this value here. So when you've got an x value, you go up here, and here's the associated f of x value. We got an x value here, you go up here and over to here. This is your associated y value. This is saying that the distance, this distance here and this distance here between these f of x values and L, we want to set to a value that's less than epsilon. All right, so I hope you digested some of that. That's why these absolute value statements are in this definition. They're talking about the distance between x and A, and the distance between f of x and L. So let's do an example using some numbers. So first we're going to write down the precise definition of a limit. So here it is. So I'm writing it with as few words as possible. So let's say it. This says the distance between f of x and L is less than epsilon, and the distance between x and A is less than delta, implies that the limit as x approaches A of f of x is equal to L. All right, so now let's define our variables. So I've got f of x from my problem statement is 5x plus 3, which is a y is equal to mx plus b, a linear function. I've got L is equal to -2. That's the value on the right of my limit equation. I'm given epsilon is equal to 0.02. And I know A is -1, the value that x is approaching in the limit. And I don't know delta, and that's what I'm going to find. So I'm going to start with my leftmost part of the definition. So I'm going to substitute in for these values here. So I've got 5x plus 3 minus L, and then that's less than epsilon. All right, and what I'm going to do is I'm going to solve this for a statement, an inequality statement involving x. So I've got 5x plus 5 is less than 0.02. So recalling some Algebra 2 stuff, I can say two things. I can say that 5x plus 5 is less than 0.02, and I can also say that 5x plus 5 is greater than -0.02. All right, so if I subtract 5 from both sides here, I get -4.98. And then I can divide by 5, and I'll get -0.996. And I can do the same thing over here. I can subtract 5 first, and I'll get -5.02. And then I can divide by 5, and I would get -1.02. 0.004. All right, now we're going to bring in the right hand. This part here, the x minus a is less than delta part. So let's write that in. So I wrote that in on both of these sides here. All right, so I know x and I know a, so I should be able to determine delta here. All right, so x on this side is negative 0.996. A, we said, was negative 1. And let's do this one over here. We've got negative 1.004. A is negative 1. All right, so let's get that number inside for both of these sides. All right, so this one's going to be positive 0.004. This one's going to be negative. Okay, we're working with linear functions. You're going to find those two numbers come out to be the same. I'll talk about that in a second. All right. So that means that's as big as delta can be. So let's say delta is got to be less than that, but it could possibly be equal to that, but that's as big as we can go. All right, so this is the value of delta we were looking for. And the one thing I was going to mention was if you're talking about a linear function, so here's your limit L, and here's the associated x value. So if we're setting our epsilon value here to be this far away from L, then this distance here, right here, and right here, these are going to be your delta distance. Those are going to be equal, and these are your epsilon distances. If it's a linear function, and that's because the slope is constant for the whole function. All right, so we found our delta value that we were looking for using the precise definition of a limit. All right, in our second problem, we're going to do another linear function. So I wrote down the precise definition of the limit. And this statement is pretty much the same as in the prior example. We're just going to do another one like that. So I'm going to go ahead and I'm going to start on the left-hand side. I'm going to plug in f of x, which is negative 3x minus 1, minus L, which is negative 16. And that's less than epsilon, which is 0.01. All right, so I'm going to go ahead, I'm going to organize this, and I'm going to solve it. So that's negative 1 plus that's 15. I'm going to solve this. And then from there, we'll find delta. All right, so I can make two true statements out of this inequality, of course. There's the first one. Here's the second one. Greater than negative 0.001. So I'm going to carry this through. I'm going to subtract 15 from the left. And I get this number here. And then if I divide by negative 3, that causes a sign flip. And I get something with a lot of 6s, that number there. Now I'm going to do the same thing over on the other one. I'm going to subtract 15 from the other side. Wait a minute, there's an extra 0 there, isn't there? Hold on, something's going wrong with the zeros. Let me fix this. Okay, got the zeros fixed. Now I've got negative 3x is greater than negative 1501. So if I divide by negative 3, that causes the sign flip again. So I get something with a bunch of 3. That's what I got. All right, so now I'm going to pull in the other side of the inequalities, of the definition, the one with the A. I'll just write it here. Let's write it here as well. All right, so I know X and I know A. So let me go ahead and substitute those in. All right, so I wrote all that down. Substituted X and A in there. All right, so if I carry out this subtraction right here, I get this. All right, so we're working with a linear function, so we expected those two numbers to be equal and opposite. So I'm going to be able to conclude that my value of delta must be less than or possibly equal to 0.00333333. And that's the value of delta that will get me within 0.01 of the limit that I'm looking for. All right, so here's another example, and the wording is a little different. It says, in formally proving that the limit as x approaches -9 of this linear function is equal to -4, we're going to let epsilon, some positive epsilon, be arbitrary. And it's asked, determine delta as a function of epsilon using the precise definition of a limit. All right, here it is. The distance between f of x and L is less than epsilon, and the distance between x and a is less than delta implies that the limit as x approaches a of f of x is equal to L. So we're going to start out the same, but since we don't have a value of epsilon, we're not going to be able to do the same approach on this problem here. So let's go ahead and plug in f of x, that's 1/9 x minus 3 minus L, that's -4, is less than some epsilon value that we don't know. It's just some positive value. All right, so this is 1/9 x, so -3 plus 4, that's plus 1. All right. So the way that we're going to do this one is we're going to make this part look like the other part, x minus a is less than delta. That's going to be our approach. We know our a, so x minus, what was a? -9. That's x plus 9. So we want to make this part look like this part. That's going to be our strategy. And in doing so, we're going to figure out a relationship between epsilon and delta. All right, so let's look at the left part now. So I can see I have a 9. So let's go ahead and multiply this 1 by 9 over 9 so we can get a common denominator. 1/9 x plus 9/9 is less than epsilon. All right, now we can factor out a 1/9 out of here, and when you do it with absolute values, you want to put this around the thing that you factor out. All right, so that would mean 1x is left in there, and then 9 would be left there. All right, so let's check it. 1/9 times x, yes. 1/9 times 9, yes. So I factored out the absolute value of 1/9, and I put bars around it because I'm dealing with absolute values. This is going to have to be positive. All right, so now what I can do is I can multiply both sides by 9. All right, and that'll get rid of that. Let's put a dot here. And I'll have x plus 9 is less than 9 epsilon. All right, let's go ahead and cross those out so you can see what I just did. Cross, cross. All right, so notice now that those two sides look the same. This one and this one. All right, now let's write that out a little closer together here. So we'll scoot it up. So let's put the other right-hand one underneath this one so we can compare them. All right, so if the left-hand sides are the same thing, that must mean that the right-hand sides are the same thing. All right, so we've got an equation. All right, so we can just turn that around if we want. We can say delta is equal to 9 epsilon. All right, so we've got a relationship between delta and epsilon. All right, now let's go back and look at the problem statement. It says determine delta as a function of epsilon. Okay, so we've done that. So that's our relationship. And we're finished. So example 4 involves a quadratic function. So we're going to apply the rigorous definition of a limit written down here. And it says if the limit as x approaches 6 of this quadratic is equal to 71 and epsilon is 0.1, determine delta. So we have an epsilon given to us this time. So we're going to start over here and we're going to plug in f of x, L, and epsilon. So we've got f of x is 2x squared minus 1. L is 71. Epsilon is 0.1. Combining like terms, we get negative 72. All right, we're going to set up our two statements. 2x squared minus 72 is less than 0.1. 2x squared minus 72 is greater than negative 0.1. All right, we're going to solve both of these for x. 72.1, 2x squared is greater than, let's see, what's that number? 71.9. So dividing by 2, taking the square root of both sides. Now we keep all these digits. Remember, when we're working with limits and approximations, do not round your numbers. Keep all your digits. So I'm dividing by 2 on this side as well. Do not round your numbers. All right, and then I'm taking the square root of that number. Wait a minute, that's not it. Hold on. 35.95. And then that 5 number is the square root of 35.95. 831886. All right, so I kept all those digits. All right, so we're down to where we have x. So now we bring in the absolute value of x minus a is less than delta. A is 6. So the absolute value of x minus a is less than delta. Both of these places here. And we're going to substitute x and a. All right, so I did the substitution there. Now I'm going to go ahead and subtract in both of those instances and find out my delta values. So those are the two numbers I get. Now I want to look for the smallest number. So I've got 165 here and 168. So this one here is going to be my smaller number. So I'm going to say that delta has got to be less than or possibly equal to 0.0041652 in order for the limit to approach within that epsilon that we're given. That's what we're being told here. Now, let's just make sure you understand why you would always want to pick the smaller one. So let me just make a quick sketch. So here's my little sketch. Let's say as x approaches a, you want to get within this degree of closeness. This would be your epsilon on one side and your epsilon on the other side, which in our case was 0.1. After getting through solving for our deltas, let's say you get one that's larger and one that's smaller. So if you pick your larger delta distance here, this one here, and you go up and hit the curve, this would then be your y value. You might be outside of the range of epsilon. So you want to make sure you pick your smallest delta value so that it gets yourself closer. If you come up here and go over to here, you're going to be within that epsilon range of your limit. All right, so you always want to go with your smaller one to ensure that you're as close as possible to your limit value. So this is our answer here. Epsilon delta must be less than or equal to that number. Do another quadratic function example. So the wording says, in formally proving this limit here, here's your quadratic, it says let epsilon greater than 0 be arbitrary. So in this example, again, we're not given an epsilon. Determine the smallest integer m such that this relationship holds between epsilon and delta. Epsilon divided by some integer m is less than delta. Use the precise definition of a limit. So here's our definition. So let's start with the left-hand side here, the leftmost side of the definition, and plug everything in that we know. So we've got the absolute value of f of x, which is x squared plus x, minus L, which is 30, is less than some epsilon. All right, and for the right-hand piece of it here, we know that x minus a, where a is 5, is less than delta. X minus 5 is less than delta. So what we're going to do is we're going to try to make this part here and this part here look the same, those two parts, so we can figure out a relationship between epsilon and delta in this form. So that's our strategy. So we got to work on this piece first. So I could see that I can factor that xx, so 5 and 6, positive, negative. So we can say that. All right, so you could see this x minus 5, that's going to match this, but we don't want this x plus 6 in there, so we're going to take that part outside here and put the absolute value bars on it to ensure that it's positive. Everything's going to be positive. Okay, and then we've got it to look like that. So now we've got the x minus 5. Well, let's put this x plus 6 over here like that, and then we've got the absolute value of x minus 5 is less than epsilon over the absolute value of x plus 6. All right, so now we've got that absolute value of x minus 5. Okay, so now if I look at the right-hand side, I want to be able to make something out of those green things that resembles this part up here, which is the statement I'm looking for. So I have to figure out what that m integer is. We want that integer m. All right, so we know that the left-hand sides are equal, and we know that this x minus 5, absolute value of that is less than delta, and the absolute value of x minus 5 is less than epsilon of x plus 6, but we want to figure out what is the relationship between this and this. All right, so I'm going to write it like that. So we're going to try to figure out how to get that looking like this here. So one thing we can say, since we still have an x in here and we want to figure out what to do about that, we do know that x is approaching 5. So we do know that x is approaching 5. So if I put that 5 down here, right there, then we can say that epsilon, that value is approaching, epsilon over x plus 6 is approaching epsilon over 11. All right, so now what? All right, but is that m going to be 11? Okay, so think about it this way. If x is approaching 5, epsilon and delta are approaching a very, very small number, almost 0. Because they're getting so close to each other as you approach the limit, that we're basically approaching an inequality here, right here. We're approaching an inequality, an equality. But we don't want it to be equal. We want it to be less than on the left-hand side. All right, so in order to make that less than on the left-hand side, that means I've got to bump up that denominator to 12. It has to be an integer, remember. That number on the bottom has to be an integer. If I bump up that denominator to 12, then I can ensure that this left-hand side is less than delta. But if I went the other way and I bumped it down to the next lowest integer, 10, I'd be going in the wrong direction. The epsilon over m side would end up being bigger than the delta side. All right, so remember, in order to make a fraction a smaller amount, you enlarge the denominator. All right, so like 1/12 of a pizza is a smaller amount than 1/8 of a pizza. Look at it that way. All right, so I'm going to say my m is equal to 12. Okay, and that will ensure me that that left-hand side is going to be less than delta. All right, so that's my answer there. M is the integer 12, and that ensures me that epsilon over m is going to be less than delta. So we have one more example to do involving a square root function. So I wrote down the rigorous definition of a limit, and we're going to substitute f of x, L, and epsilon into this leftmost piece. So I've got f of x is the square root of x minus 5, and L is 4.4214, and epsilon is 0.1. All right, so out of this I'm going to get two statements. The square root of x minus 5 minus 1.414214 is less than 0.1, and then of course we've got the other statement, greater than negative 0.1. All right, now we're going to solve these for x. So if I add that number over to the other side, I get 1.514214. And if I add that number over to the other side on this one, I get 1.314214. All right, now I'm going to square both sides like this to get the root out. All right, and I'll get less than 2.292844,038. And over here, same business, square both sides, and I get 1.727158,438. All right, now I'm going to add 5 over to the other side, and there we go. So I've got those two values of x. Now I go ahead and I bring in the other side of my definition here. The x minus a is less than delta. So let me just put it in both of these places here. All right, now I have an x value for both sides, and my a from back at the beginning was 7. A is 7. So I'm going to substitute a and x into both of these absolute value bars. All right, so there's my substitution. Then if I go ahead and carry out the subtraction, I'll get the following numbers. There they are. Now, because we're looking for the smallest one, I'm going to choose this one here. This number is smaller than this one, the absolute value. So let's write that down. So there's that number. So we conclude that delta must be less than or possibly equal to that number in order to be within the value of 0.1 from the limit. So that's my answer. So once again, when you get two different numbers for your bottom line here, you always want to pick the smaller one. Okay, so that wraps up our examples for the rigorous definition of a limit. So now we'll attempt some homework problems and see if we can make some sense out of how to do these problems.